0.5 of a 1, okay? But the expected counts do not need to be whole numbers because expected counts, think about like the perfect scenario, okay? If we were to roll a dice 60 times, we would think in a perfect world, each number would be rolled exactly 10 times. So it says to measure the difference between the observed and expected counts and determine if the difference is significant, we will introduce a new test statistic called Chi Squared statistic. Okay, so Chi Squared, it's a fancy X, is equal to the summation of observed minus expected counts squared divided by expected counts. The sampling distribution of chi-squared statistic is not a normal distribution. It is right-skewed and only allows for positive values, which means chi-squared can never be negative. When the expected counts are all at least 5, the sampling distribution of chi-squared is close to the chi-squared distribution with degrees freedom equal to categories minus 1. Okay. So everything that I just kind of said, it repeats right here. So it's the number of categories minus 1. Okay, so if we think about the number of categories for the dice, well, there's 6 different sides, so there's 6 categories. Minus 1 would give us a degree of freedom equal to 5. Okay, now we're going to talk about how we can compare observed and expected counts based on how close or how far apart they are. So the chi-squared statistic compares O and E, observed and expected counts. So if observed and expected counts are close together, which means their numbers are close together, this is going to give us a small chi-squared, but a large p-value. Okay, chi-squared distribution looks something like this. And this first part right here would be chi-squared, with everything shaded being the p-value. Okay. If we have a large p-value, that means we're going to fail to reject the null hypothesis, which means our conclusion is a good fit with the claimed distribution. So it's a good fit. If observed and expected values are far apart, then we're going to get a large chi-squared value, but a small p-value. Okay, that means on the chi-squared distribution, our chi-squared value is now this small shaded region. If we have a small p-value, we're going to reject the null hypothesis, which means we don't have a good fit, so not a good fit. Okay, so now talking about the hypotheses. Says the null hypothesis in a chi-squared goodness of fit test should state a claim about the distribution of a single categorical variable in the population of interest. We can write it in words or symbols. Both are accepted and used on the AP exam. So let's go ahead and write an example of these null hypothesis by using the fair dice example. So one way you can write this is talk about all the different proportions and how they're the same. So the probability of rolling a 1 is 1/6. Probability of rolling a 2 is 1/6. Okay, all the way to the probability of rolling a 6 is 1/6. Okay, where P1, P2, all the way to P6 represents the proportion of outcomes of the die. Okay, so that's one way you can do it. Typically, you would use this way to write the null hypothesis if all your proportions were the same. If all your proportions were different. Okay, The reason for that is if all your proportions are the same, then why not just write it in a sentence that states the proportion of dice outcomes is equally distributed, instead of having to write P1 is equal to 1/6, P2 is equal to 1/6, etc. Okay, the alternative hypothesis is always going to be this same sentence. We are always going to write at least one of the claimed proportions are incorrect or wrong. Okay, always we'll write it this way. Now let's look at our conditions. So we still have random and independent conditions. So random means we have a random sample or random assignment. Independence, we're using the 10% condition. Okay, and then for our quote-unquote normal condition that we used to prove, since chi-square distribution is not related to the normal distribution at all, we're going to use what's called large counts. And for large counts, we just need to see this. All expected counts are at least 5. Okay, if it is, we write that sentence. If it's not, then we say not all expected counts are at least 5. Okay, what this implies is this allows us to say that the sampling distribution will follow a chi-square distribution, which means we can then find the chi-squared test statistic. So in these notes, we're talking specifically about chi-squared goodness of fit test, GOF test. It says when the conditions are met, the chi-squared goodness of fit test can be performed with the hypotheses. So either that the null hypothesis states the claim of the distribution is correct, and the alternative saying that one of them is incorrect. So claimed is correct, claimed distribution is incorrect. We find the expected counts, assuming the claim distribution is true, and then we calculate the chi-square statistic. Okay, so that's chi-squared is equal to the summation of observed minus expected squared, all divided by expected. And then we would find the p-value, but I'm going to have you guys just cross this out. Okay, because we're not using the TI-84 here, we're using Desmos. So when I show you the example on Desmos, I will show you how to find that p-value. Okay, then it says beware, which means these are some very common mistakes. The chi-square test statistic compares observed and expected counts. Don't try to perform calculations on the proportions. When checking the large counts condition, be sure to examine the expected counts. So large counts is for expected counts, not observed counts. Okay, so now let's look at the example here, and we're going to do our 4 C's. So it says that a geneticist is studying the gene pattern of eye color in a group of white mice. Okay. He observed a random sample of mice from a lab and found that 110 had red, 57 had brown, 32 had pink, and 13 had blue eyes. His model suggests that the distribution of eye color should follow a 9:3:1 ratio. Is there evidence that the geneticist model is not accurate? Use a 5% level of significance. Okay, so the first thing we're going to do here is we are going to do our communicate. And in communicate, we're going to label our hypotheses. So our null hypothesis is going to be based off that ratio that they give us. So it's a 9:3:1 ratio. Well, if I was to take all those numbers and add them together, I get 16. So that tells me that red, which is the very first type of eyes it mentions, so the probability of red eyes is going to be 9 out of 16. The probability of brown eyes is 3 out of 16. Probability of pink eyes are also 3 out of 16. And the probability of blue eyes is 1 out of 16. Okay. Then my alternative, which is always going to be the same, is stating that at least one proportion is incorrect. Okay. Then the next thing I'm going to do is I'm going to create a table that has my observed and expected values. So I have red, brown, pink, and blue. And then I have my observed and my expected. Okay, so my observed is part of the problem. That's the 110, 57, 32, and 13. And my expected is the total trials of mice. So if I was to add all of these numbers together, I would get a total of 212. So it's that 212 times the proportion of each of the colors. So for example, 212 times 9/16. Okay, 212 times 3/16. And 212 times 1/16, which gives me 119.25, 39.75, 39.75, and 13.25. Okay. From here, I'm going to do my conditions. So first with random, in the problem, they said they had a random sample of mice. Okay, for independence, I'm using the total number of mice, so 212, and say that is less than or equal to 10% of all mice, which is a safe assumption. And then for large counts, I'm going to go back and I'm going to look at all my expected counts. Okay, so all the ones I calculated, and I'm going to ask myself, are they greater than 5? And since they are, I'm going to say all expected counts are greater than 5. Okay. Then I move on to calculations, and I'm out of room. That's okay. I'm just going to go up here and erase some things for space. Okay, so calculate. Oh, that looks like pretty messy. Okay, calculate. I'm still going to write the name of my inference. And so this is a Chi Squared goodness of fit test. So what I'm going to do is I'm going to go onto Desmos and I'm going to click the plus sign. I'm going to go to inference, and then I'm going to go down here under categorical data and click on Chi Squared goodness of fit test. Okay, then it's going to have me type in my observed and expected values. These are the values that I found on this chart here. So observed, I'm going to have to zoom out to type in some numbers. There we go. Okay, so 110, 57, 32, and 13. Then I go to my expected, and I do 119.25, 39.75, 39.75, 13.25, and hit create tests. We're going to drop down right here where it says significance test, and notice I have all my answers here. Okay, it gives me my chi squared value of 9.719. It gives me my p-value of 0.021. It gives me my degrees of freedom of 3. And the last thing I would add here is my 5% significance level, which is alpha equal to 0.05. So once I have that information, I can now write my conclusion. So my conclusion, I'm going to be comparing my p-value to alpha. And since my p-value is smaller than alpha, I'm going to reject the null hypothesis. So since p-value equal to 0.021 is less than alpha equal to 0.05, we reject the null hypothesis. Okay, which means we have convincing evidence that the geneticist model is not accurate.